welcome back from from your coffee and the break. So the first talk of this session, or last session of the MAYA meeting, will be provided by Joris Witstok. So his title is Dual Constraints with ALMA, New O3 88 micrometer and dust can reveal the ISM conditions of the luminous LBG at super high redshift, about 7, about 7. So Joris, I will give you 3 minutes warning with my little notes, and now take it over.
Okay, thank you. And thank you very much to the organizers for putting up this really great meeting. So yeah, today I'll be talking about some work we did with ALMA. Was published last year in collaboration mainly with my now previous supervisors, so Renske Smit and Roberta Maialino. Currently I'm a postdoc still at the Kavli in Cambridge. And then this was also done in collaboration with all these people spread over other institutions. And so really the main point of this work was to look for the oxygen 388 micron line in these very high redshift galaxies, and simultaneously also to constrain the dust emission in these systems. So just to put it into context, and this is really the story just before JWST was launched. So sort of a year ago, we when we wanted to do spectroscopic measurements of really high redshift, so probing the epoch of reionization galaxies, if you wanted to reach the rest frame optical from the ground, you were basically limited to a redshift of about 3.5. And you could go to the rest frame UV and look at some of the weaker metal lines. If you want to look at even the brightest UV line, Lamin alpha, that will start to get mostly absorbed by a redshift of about 7. And so this was really the best we could do with current instrumentation, but we already were able to probe deeper further back in time with ALMA, mainly using these two emission lines, so the C2 158 micron line as well as the O3 line. And this is a really powerful combination. And so just to again illustrate this point a little bit, so in this figure, this is as a function of redshift, the observed wavelength of the rest frame UV lines, and then the rest frame optical. So with JWST, we now have the rest frame covered up to very high redshifts, and of course, we've seen a lot of spectacular work over the last year from this aspect. But in this whole picture, ALMA really has a very complementary role to play. So there's all these far infrared emission lines that we can probe with ALMA to get, as I said, a complementary view of these very high redshift galaxies. And so before JWST, we had about as many UV bright galaxies that were being confirmed through ALMA, through the C2 line, as, for example, with Lyman alpha. And what's really nice about ALMA, of course, is that you don't only get spectroscopic information, but you can really map out spatially the signal from these systems. So in this case, I'll be talking about, as I said, a new sample where we observed the oxygen 388 micron line. So this is a sample of 5 galaxies that were first confirmed in C2 and then followed up with oxygen 3. And in one case, we also observed the nitrogen 2 line, which we didn't detect, however. And just to very quickly mention what these systems are like, they're quite UV bright, which is how they were selected. But at this redshift, they're actually normal star-forming galaxies with star formation rates of about 20 to 60 and stellar masses of a few times 10 to the 9. And then the way they were selected was to have medium to high equivalent widths in the optical lines, which then you can see here provides this excess in the Spitzer bands, which then gives a very tight constraint on the photometric redshift. So this allowed ALMA to really efficiently scan for the C2 line in the first place. So just to show you what the new Auction 3 data looks like. So this is in red, showing the Auction 3 emission overlaid on the rest frame UV with seen with HST. And you can see that in most cases, these systems, they have a bit of a clumpy morphology, and the oxygen traces quite well the bright rest frame UV, but there's not a perfect one-to-one overlap between the two. So for example, here you see that even though there's two clumps seen in the UV, the oxygen really only seems to come from this one clump. And as I mentioned, we simultaneously get constraints on the dust continuum emission by looking at the 90 micron continuum. And even though we don't detect emission in all of the 5 galaxies, in fact, we only detect it for 1, we still get some interesting constraints on the properties of the dust in these galaxies. So this is just an overview of all of the data we're working with, the emission lines at least, so the C2 and the O3. So O3 is again shown by the red, and then C2 is shown in the blue. And you can see already that these trace quite different phases, so that the C2 in general is a bit more extended, as it's thought to trace the more colder and neutral gas around these systems. Okay, so what can we look at? Well, one natural thing then is to look at the ratio of O3 to C2. So that's what I'm showing in these figures on the right. So if you just focus on the top panel here, this is the ratio as a function of, again, the equivalent width of the optical lines, which is basically an inverse tracer of the age of the stars. And so you see there's this nice correlation. The gray points here are local metal core dwarfs. And you see that basically the younger the stars are, the higher this ratio is. So we try to have a look at photoionization models to see if we can reproduce these values in very simple models. And indeed, if you, not very surprisingly, if you take a young stellar population, you see that if you use fairly high ionization parameters, you can nicely cover this area of the parameter space. However, if you then look at the oxygen 3 line in particular, so that's shown in the bottom here as a ratio of O3 to the star formation rate, then things get a little bit more difficult to explain. So basically, these models here, and especially the orange line, are quite high metallicity models. And you see that for some of the measurements, they don't quite seem to match up. And so the Auction 3 is really brighter than we'd expect, even for the most metal-rich models that we use here. And so in principle, this would suggest that the metallicity is actually quite high from just the O3 luminosity. And of course, there could be some other things going on that we don't quite understand. The photoionization models might not fully capture the complexity that's at play in the ISM of these high redshift galaxies, but it is something really interesting and possibly telling us that, yeah, there's something we're missing here. So then in the final part, just to talk about the dust properties, I think going this far back in time and looking at the dust emission and seeing if we can tell something about the properties is really interesting, because at these very early times, we really start to probe the first buildup of, first of all, metals and then their conversion into dust grains. And you can start to compare, for example, what the theoretical yields are for sources of dust production. So these are mainly thought to be AGB stars and supernovae. which are thought to produce mainly supernovae, really, about 1 to maybe 2 solar masses per event. And second of all, we expect to find higher dust temperatures, which is quite simply explained because you just have higher specific star formation rates. So you have more younger, more massive stars that are heating up the dust in their surroundings compared to lower redshift. And so that heats up the dust more efficiently. So what can we tell from our measurements? Well, as I said, the O3 probes the dust emission at 90 microns rest frame. And so in combination with the 160 micron, which we have from the C2 measurements, we can start to constrain the shape of the SCDs. And really, we only have 2 points, of course, but we can already start to rule out some of the configurations in this case, so some of the more extreme properties. And actually, in this case, for example, the upper limit at 90 microns is even so constraining that we can start to rule out some of the hotter dust in the system. So if we look at the dust temperature as a function of redshift, so seeing how it evolves over redshift, then as I mentioned, you see this general trend of increasing dust temperatures towards early times. And the colored points here are the systems that we can constrain with our measurements. And you see that especially this blue point here, which I just pointed out, really has a surprisingly low dust temperature. But you also see that there's a lot of scatter still. So we really need to get more data and really try to understand what's going on. I think one clue that we already have from this data set is that if you look at the 2 different bands, you see that at 160 microns, there's this very prominent extended emission, while at 90 microns, at shorter wavelengths, it's really only this compact core. And this is telling us that the compact region here mostly has the hotter dust. And so it might be that actually there's this more extended cold dust reservoir. So it's not really well explained by just one component, but it might be more of a dust temperature gradient across the galaxy. And this one source in particular with the low dust temperature also implies that there's actually a really high dust mass. And this really is in quite a significant tension with stellar production models. So we seem to be needing 4 solar masses per supernovae, which, as I said, is way above the theoretical expectations. So this might be evidence that either we are seeing a different kind of dust production scenario at these very early times. And so potentially it could be the IMF, or there's just other production mechanisms of dust that we're starting to explore here. And there's a new program which, we hopefully will get some data for very soon to look at even more different wavelengths to really constrain as well as possible the dust temperature and thus the dust mass in this system. So finally, just showing some preliminary work that should be hopefully on the archive soon. So here we looked at a slightly larger sample of galaxies at the highest redshifts, really, so redshift 4 to 8 roughly. But we selected those particularly where we do have already in the archive multi-band dust continuum detections. And so for these systems, we can really accurately model their far infrared SEDs. And this is just showing you the evolution as the beta parameter. So this is one of the parameters explaining the shape of the far infrared SED. And you can see that comparing to low redshifts, the local samples, there doesn't actually seem to be very much evolution in this parameter, at least. what is interesting, and I won't go into the full details here, but if you look at, again, the dust masses of these systems versus the stellar mass, then for these systems where we can actually really accurately measure the temperature and the dust mass, they still seem to be quite inconsistent with sort of your standard yields of dust. And so, again, this is probably pointing out that there's something here we're missing about the very quick production of dust. And then finally, again, if you look at how the dust temperature looks in these systems, you again see this increasing trend, but it does seem like most systems do follow this more gentle evolution in the dust temperature. So they're not getting extremely hot dust as you would expect in some theoretical models, although there is still quite a lot of scatter, which just may be pointing at an intrinsic scatter in this quantity. So I'll just stop here at the conclusion. So I've presented a new sample of star-forming galaxies at redshift 7, where we see quite diverse and also spatially varying O3/C2 ratios. And I showed you this trend with the equivalent width of the optical lines, which is also seen in local metal poor dwarf galaxies. And surprisingly, it seems like a few of the systems seem to require quite a high metallicity to explain how bright these O3 lines are. And then finally, I've told you about the dust properties in these systems, and how in one of them we seem to really need a very low dust temperature coupled with a high dust mass, which is indicating that potentially the build of metals and also conversion into dust is more efficient than we might have expected. So I'll stop there and happily take any questions.
Thank you for nice time control. We already have questions. Just speak up. Cardinal?
Yeah, thank you for this talk. I have just a quick question. How, I'm not an expert, but how can you exclude the presence of AGN activity, for example, from just the line ratio that can cause the boost of the dust temperature raising sources? And related to that, sorry, just a related question. When you, I don't completely understand the argument that you expect higher dust temperature just on the basis of the higher star formation rate expected at high redshift, because just from the star formation rate density history that is poorly constrained at high redshift, but it has a peak at redshift about 2 at the cosmic noon. So I expect that the star formation rate decreases, and this decreases with redshift.
Yeah, okay, thanks. Those are really good questions. So on the AGN aspect, I think the very simple answer is we don't know. We can't tell with the current measurements. So until we had JWST, actually, we could only really probe the rest-area UV, as I mentioned. And so for these systems, all we have is the photometry. But you can tell, for example, in some of these, that just from the line widths, they're actually quite broad. So that might be an indication that, what we're really seeing is just low luminosity AGNs. You can't, I wouldn't say you can conclusively say anything about AGN activity just from these far infrared lines. So you'd have to go back and ideally look at the rest-area optical or the rest-area UV to see if you can measure any typical AGN features. Then as for the dust temperature question, so again, it might be that there is actually AGN activity, of course, in these systems. What I will say is that, so what I mentioned about the the increase that's expected just from the star formation perspective is that it's really the specific star formation rate here that is increasing towards higher redshift. So you're getting more younger, younger stellar populations, which are more efficiently heating up the dust, if that makes sense. There's a lot of work showing this.
Yeah, I'm also thinking that probably these sources are smaller on average, so the contribution of the
exactly more compact. So yeah.
Thank you.
Right. Last question, Roman.
Yeah. Well, thank you first. It was very interesting, and I was wondering because you mentioned that the modeling of the ISM may not be able to reproduce the complexity of the oxygen-free emission. So would you say that the modeling is overestimating oxygen-free always, or just in general not estimating it well?
I meant in this case mostly, so the plots I'm showing here are just simple cloudy models. So really what I was trying to say is that in cloudy, you just assume basically one single component, one single cloud. Whereas in reality, we know from high redshift galaxies that they're very messy, and you have all these different components, star forming clumps. I was just trying to say in measuring these different phases, we have to be careful that we can't just assume all the light is coming from the same, single cloud, as you're basically assuming in some of these simpler models. So I think the only real solution for this is to go to simulations, and that is something, of course, that's being worked on. So yeah.
Thank you.
Cool. So we can surely propagate more discussion in the Zoom chat or Slack chat. So I was just sorry.
That's okay. Thanks.
For the interest of time, we have to move on. Right. Cool. Thanks, Joris. It's a great talk.